Hey everyone, welcome back. So we're now in chapter 5, which is about diffusion. Diffusion. So you might be wondering, what is diffusion? Or how does diffusion occur? Do we see this materials processing? All these questions will be answered during this chapter. So first off, what is diffusion? Well, it's mass transport by atomic motion. Mass transport by atomic motion. For gases and liquids, that's just random, which is called Brownian motion. It's just they're bouncing into each other and moving around each other. That's all great. But what we really care about in this class is the solids aspect. And how does that happen? Well, that's through either vacancy diffusion or interstitial diffusion. Wait a minute. Vacancies, interstitials, that sounds familiar. We've heard those words before, haven't we? We have. Now you might be understanding why in chapter 4 we started talking about all of those different impurities. We have interstitial atoms which are able to fit through or inside of the gaps between other atoms, and vacancies where we have gaps where we should have an atom. I also mentioned that those vacancies can move, and diffusion is that process where it goes from one state to another state. And it's the atoms that are moving, but it looks like the gap is moving. We're also going to care about interdiffusion, where we have diffusions of atoms of one material into another material. That's not saying necessarily interstitial diffusion. That could also be like a completely solid solution, where you have A and B, and then eventually they get mixed together into some mixture of A and B. This is also what we learned about those Hume-Rothby rules to figure out when that could happen. And finally, there's self-diffusion, where we just say, well, honestly, there's a big mass of atoms. They're all the same kind of atom, but they can just move around. They can switch places, and we don't really notice that all that much, but it happens. Okay. So what we'll find is that atoms tend to migrate from regions of high concentration to regions of low concentration. It's kind of like air pressure. If you've got a whole lot of high pressure air in one room, or water, let's just say, and I open that door, I swing it open, if the door is open, well, it's going to suddenly start flooding in there. It's going to go from where there's high pressure on one side to low pressure on the other. And it's very similar in this case. They're not going to keep this perfect line. It's just not very statistically possible for that to happen. Because of the random nature of the movements, they're eventually going to start mixing into each other. And we go from these very, very sharp lines to these nice, smooth concentration profiles. So from that sharp profile to the smooth concentration profile, and it's going to happen over some period of time. Now, with self-diffusion, it's simply the atoms within that material are moving. So you might have A, B, C, and D like they are on the left, and after some interval of time, they've moved around. Now, how do they move? Well, they need vacancies. Honestly, they need some gap where there isn't an atom so they can all move around. And there's always vacancies because if we increase our temperature, vacancies form, and unless we go down to very, very low temperatures, we're going to have some sort of vacancy there. So that's it for this time. We learned about diffusion, which is mass transport of atoms. And we learned just basically that diffusion happens because we want to go from high concentration to low concentration, and sometimes just because atoms move. If you're a big mass of atoms, they're going to move. If you're in a room with a bunch of people, you're probably going to wander around the room. So, thanks for listening, and I'll see you all next time. Bye-bye.